Hello everyone, thanks again for all the really helpful comments in the last video. I find it so useful to read through them as everyone has experience and expertise in different fields. Yes, there were quite a few commenting on the details of using toilet paper. And also some expressing the benefits of resonant humming in toilet cubicles, each one having its own unique frequency which increases the amplitude of the humming when you hit that sweet spot. I don't know if it's just humming noises this applies to, or if there are other noises that might have this special effect, but it's all interesting stuff and also quite amusing. Moving on, I decided to have one last attempt at positioning the driveshaft shroud so it doesn't contact. And the broken leg I've temporarily replaced with a previous part that I used 3.2 mm wall tubing. It was the 1.6 wall leg that I later changed that broke. Some really good ideas in the last video on a better design which I will investigate and report back. I might have finally solved the exhaust cracking issue. Look how much movement there is on the exhaust as the engine idles. The exhaust was always rubber mounted and had a flex joint, but I've now made it so the exhaust can move more freely. I think rubber mounts didn't allow enough free movement. The brackets that were holding the exhaust suffered the same cracking issue as the 90-degree bend. The first liftoff back in February 22 resulted in a broken exhaust mounting, and I've repaired it numerous times since. Let's hope my change has sorted it. Right into the first run then. The plan is to listen for driveshaft contact and maybe take it up to light on the skids if all goes well. I'm able to hear if there is contact, so don't need to refer back to the video. The reason I'm flicking the master switch on and off here is because the battery is flat. A reoccurring broken cable near the voltage regulator has again broken. A quick fix and cable tied in another location will hopefully solve this issue. The battery drains really quickly without the alternator as it's a small battery. I did notice the volts were lower than usual during the test. Driveshaft still feels good, so onward and upward. With the new CDI unit, the engine starts nice and easy. Now I want to start lifting off a bit more, get a feel for it again as it's been a couple years since I last hovered this machine and I'm going to be rusty. I didn't get far off the deck, but enough to get a feel for it. It seemed to take a long time to spool down for some reason, maybe getting some temperature into the bearing grease. I like to let the blades come to a complete stop before getting out. I could hear an unusual tinkling noise. I don't think it was the driveshaft contacting, but decided to mark the edges of the roller guides just in case. Run 3 now and hoping to make some progress. During my inspections, I did notice some play on the universal joint yoke. Nothing on the steel one. I'm confused by this as I know both are the same dimensionally. I have to investigate this, but for now I'll add a 0.1mm shim on both sides. I don't know if you noticed, but there was a single point in that clip where the drive shaft did contact. However, this is dwarfed by another issue now, which is the drive shaft binding. It was getting hard to operate in pitch, but I'm not happy with it in roll either. So this drive shaft I've taken off and it's free there, but if I start to apply some torque, now it's starting to bind, and there you go, look. There's definitely a problem with one or more bearings. Let's see if we can find out which one. Nothing obviously wrong with that one. I'll give it a measure. That measures 0.01 over. So that hasn't increased. Nothing wrong with that. 0.3 there, that's okay. This is the second one, and I can just about see some denting. It's on this end, not this side. Get the camera to pick that up. You can just about see it in the light there. But the diameter hasn't increased. So it's not too severe. This is the worst one so far. You can actually see where it's been sliding there. That's what was jamming. This one is increased by 0.02 of a millimeter in diameter. So overloaded. Just come to this last one and I can't get E off at all. The conclusion then, these aren't going to work. What are my options then? I could go to a slider, make something that's low friction. It was suggested in the comments actually to try some low friction material as a slider. That's one option. The other option is to choose a different type of bearing which is designed to be run on a flat surface. These are not. They're designed to be pressed into a hole. In order to fit that type of bearing inside here, these slots would have to be wider, and then these get bigger, they get heavier, and then it might be better to choose another option entirely. In the last video I showed a ball spline which I can purchase. It's not a huge amount of money. It would mean the attachment here would have to be changed. I'd probably have to make a new universal joint to fit a different size tube or shaft. So it's not a 5-minute modification, but
I suspect it would last a very long time.
As mentioned, JLCMC sell a variety of ball splines and I've decided to get one. I'm going for the non-flanged nut type and a solid shaft. They do sell some smaller hollow shaft ball splines too. The maximum shaft diameter is 30mm, but I'm going for a 25mm and they supply shafts up to 1 meter long at this diameter. As you can see, it's incredibly good value for money. There is an option to have 2 nuts on one shaft, and in doing that the maximum allowable torque goes up massively. As the nut only weighs 400 grams, I thought that would be a sensible option. All you have to do is specify 2 nuts at checkout. It is well packaged and very nicely made. The nuts have a plastic end cap where I imagine the balls recirculate. The nuts move freely and I can't detect any backlash. I think this is going to be absolutely perfect. I'll do an assembly drawing later in the video to show how this is all going to connect. Thanks so much to JLCMC for the ball spline and sponsoring this video. Check the description for a link to the website and coupons.
I come to realise that that is not the only issue. What I noticed was the force to go left or right or roll is too stiff for me to get any better at hovering. What happens is if you want a small amount of movement, that's okay. I mean, what you need to be able to control a helicopter is very small but quite quick movements, and if it's too stiff I can't do that quick movement fast enough, so I can't correct fast enough in order to keep control of it. The forward and backward, it's easier for me to go forward and backwards just because it's easier to push and pull from this position, whereas left to right, where I've got my arm fully extended, it takes more force. Now the ratio of pitch and roll is the same in both directions, but I'm thinking I might change the roll ratio to make that easier, and that might make the difference. I could do both the same so that they are both easier, but maybe only roll is required. I think that is the only way I'm going to get any better at hovering, is changing this ratio. If we look at early Igor Sikorsky's videos, his stick movement is massive and he's still able to control it quite well, so I can improve this. What I was going for is a sort of similar amount of movement as a Robinson. I wanted the control to feel roughly similar, but it looks like that's not going to be possible with the design I've chosen. A lot of people will be saying I should have gone for collective and cyclic pitch. Well, yes. Had I been in the position I am now with the experience of building this instead of nothing, then I would have done that. I didn't. The problem is to change this to cyclic pitch and collective is a huge amount of work and probably quite a few years. Changing the left to right ratio is quite simple. I just need to make another one of these bits of tubing here so that they're not sticking out as far. You can already see that I've modified this once before, so I put more bend on this to come back inwards. But actually, if I made a new one to take this bar from there to there, both sides, that would change the ratio. You can either do it down there, or you can do it up here by increasing these so that they're bigger. You can already see that the rods are tapered, and they will taper even more with the change in ratio. This is the full travel in row I currently have. So there is a little bit of scope to increase this before it starts hitting my leg. There's something that's been playing on my mind for a while, and that is the design of these blade straps. Now the situation here is I've got a single bolt there and 2 M8 bolts there. So that's 1/2 inch, that bolt hole, and these are 2 M8 bolts. The width of the material is 44.4 millimeters wide. So I did a calculation on the tensile strength potentially of this blade strap, so I just added up the areas between the holes. That came to 0.348 inches squared, and the material was 7075 T651 aluminium, and 1 inch of this material can take 75,000 pounds of weight before it breaks. So if we take the cross-sectional area, it gives a figure of 11.4 tons that would take. That's if this was all in one piece. That is not the case when you've added up 3 sections with a hole in the middle, because holes are a stress riser. What I want to know is, what is the actual braking load this strap can take? Now that 11.4 tons is one blade strap. We have 2, so that's 22.8 tons should be able to take. The centrifugal force on the blade is 2.8 tons, so there is a big safety factor, but like I say, I don't know how much the strength is reduced by adding those 2 holes, so that is what I want to know. To find out that information, that is why I've got this machine. It's a tensile tester, and I've just put a digital gauge on this. This machine is new to me, the first time I've done anything with it, by the way. So it had 2 of these old-fashioned gauges, and that one still actually works. It's been left outside for a while, so it's got a bit rusty. We can see the red line there. That is 20 tons at just below 750 psi of hydraulic pressure. That is the maximum this machine can take. The digital pressure gauge, that one records the maximum pressure. So when it breaks, I'll get a figure to go by. I've already done some tensile testing with it. This is just 1 mil steel, just to see where it breaks and how it breaks, really. This one I did actually calculate. I thought it would fail at 50 psi, which is 1.2 tons. It failed at 43 psi, so it's a bit lower than I predicted. These I just pulled apart just to see where it breaks first. So these 2 holes are spaced exactly like my blade strap, 22 millimeters apart, and it broke from the edge first. This was another one here where I put the holes closer together and it broke in the middle first. So depending on where you have the holes depends where it breaks first. So you can look for cracks in the right place. That was the idea. Now this is the remainder of the blade strap material. So what I'm going to do is I'm going to cut this section off, mill it down to 44.4 millimeters width, drill 2 holes 8 mil, and then we're going to see how much force it takes to break. That result is confusing. It broke at 14 tons or 31,000 pounds, and I predicted that the maximum it would break at is 26,000 pounds or 11.8 metric tons. I was expecting it to be a lot less than 11.8, but it seems it's 14. I've checked the calculation. I don't understand. I'm on the right side, of course. 14 tons is a very good figure, seeming as though we've got 2 blade straps and the centripetal force is only 2.8 tons. Just goes to show that this 7075 at 75,000 psi is really strong aluminium. Mild steel is 63,800 pounds per square inch. Really strong stuff. Here is the plan. Inside here are the 2 ball spline nuts, and they're located to the tube with a keyway. You can see the key there, and that goes down to this hole. I have to drill a hole in the tube because you can't broach a keyway without it going into a hole or going out the other side of the tube, so I have to drill a hole in it. There are keyways on both sides, and that's so that the imbalance is taken care of with having a steel key sticking out into this aluminium tube. On the back side of the top yoke, what we've got is milled holes or half holes, and there'll be pins going into that, and the pins will be held in place by a washer going on the back of here, which I'll have 4 M3 screws holding that washer on, so the pins
The pins can't come out. On the other side of here, I'll turn the shaft down so that this spigot comes through here, and there'll be a circlip holding that one on, so that can't come out. You can see the travel there. We turn that around. We can see the spline shaft goes inside that tube there. The whole assembly weighs 2.8 kilograms, which is about 500 grams more than the last drive shaft. But that is really because I've got two nuts. Those nuts are about 500 grams each. So that is where the extra weight has come from. But I think two nuts is going to be a lot better of a shaft than just having one, although one might do it. I'll sort this drive shaft out, make a new top universal joint and the connection at the bottom. Shouldn't take that long. And then in the next video, I should be able to continue with the mucking around. I think that's all I've got to say. That it? Yep.